So hey guys, we are back with another video, and in this particular video we are going to talk about DeepSeek-V3. So this video is going to be quite long, right? It is going to be of around 30 to 35 minutes. At least that is what I'm planning to do. Uh, we are going to cover all the major aspects that make DeepSeek-V3 what it is today, right? And maybe in the next video we can talk about how DeepSeek R1 came into origin, right? With techniques like GRPO and everything. So this video actually focuses on the five main aspects of DeepSeek-V3 that we're going to cover, and I'll try to keep it as short as possible and more informative, so that I think people are going to stick with it, because I've seen, right, people making 3-4 hours long video. Most of the people who don't stick to it till the end. Try to keep it short and informative, okay? And maybe if some particular topic you feel needs to be discussed more, we can make a separate complete video about that, okay? Start. So coming to what exactly is DeepSeek V3. So it's a 671 billion parameter model by DeepSeek, and they have already released two models before this, V1 and V2, and they did not get as much attention as V3 got. And the best part is the scale and performance of this model, right? We have all heard that, okay, this was as scalable, by 10 times or 15 times than the original GPT models, the big models that are currently in the market. Then it is open source, it is core, and it has competitive performance when you keep it across models like GPT-4o, Claude 3.5, Sonnet, and even in some cases it is surpassing them. That's a big thing, right? I think when it comes to parameter part, a lot of people don't realize, but they decreasing because people are coming up with new techniques through which you can have less parameters and still achieve good performance, right? Recently, I think in an Nvidia summit, right, I think we got to know that GPT-4 is a 1.8 trillion MOE model. I think that was for GPT-4, right, not 4o. So that was one leak I remember, right? So yeah, let's deep dive into the five aspects. So the five things are: multi-head latent attention, mixture of experts. It's not a traditional mixture of experts. We are going to talk about it. Multi-token prediction, quantization, and rope. I think rope and quantization and multi-token prediction, these three things, I think, okay, rope, quantization, and mixture of experts, these three things, I think most of the people have already made videos about, but okay, we are going to cover everything. Multi-head latent attention, it was a concept that was introduced recently within the last like 1 year. It got famous. I think few months had passed. And then multi-token prediction, it was also a concept that was released recently, and they have used it. So it's cool, right, that they are actually looking at the latest processes that are making speed and performance good, and they are implementing that and making that model open source. What more good can happen, right? Now let's talk about multi-agent attention, okay? So okay, I'll be looking throughout the whole PPT, right? This whole presentation, I'll be looking through my notes so that I am able to deliver you guys what I had in my mind when I was studying about this, okay? So the main aspect of this whole thing, right, it was designed to improve the efficiency, particularly in terms of memory usage while maintaining the performance, okay? So they incorporated MLA not only in DeepSeek V3 but also in DeepSeek R1, right? The reasoning model, which is one step ahead of the current V3 model. And the whole concept relies only on two aspects, right? Okay. So the scale dot product attention, right? This is the multi-head latent attention's main part, right? We all know it's a very simple process, right? When we talk about it, we have the whole value, key, and query. Now we have the linear concatenation that is done at the end, and in between we have the scale dot product, right? And the whole concept relies on this whole small thing, right? This small architecture that we think is the main core of the whole transformer architecture. The multiplication formula of the whole attention, right? That you take the softmax at the end of all things, and then you do the math multiplication, okay? But DeepSeek came with one concept which is quite similar to it, but they have made some minor, not I would say minor changes, but a good level changes, which can actually change the performance and inference speed, okay? So this is how the group query attention looks. So I think you guys know this is multi-head latent attention, this is the group query attention, right? Now came the concept of multi-head latent attention. I have given these 4 points because I personally think if you understand these points, everything is done. They make the whole KV cache thing smaller. So I think people who don't know about KV cache can go and watch my video. I'll pin down that video in the description as usual. So KV cache, basically, you don't need to every time calculate the tokens for which you have already done a calculation, right? So you can store that cache with you. Now, because the multiplication goes like this, right? You have this metric, then you have this matrix, and then you go one by one. Okay. So they see that they have made this whole KV cache smaller. They see no lack in the performance, and they have applied this low rank matrix to represent the key value pair. The only important point, right? You see here the key value pairs. They have used this whole concept of low rank matrices, okay, and it is used in both inference and training. So if you look at this diagram, that you will realize, right, that this they are representing this key value pair that we were talking previously about using this low rank matrices. And you must be seeing that, okay, they have done that, but post that they have applied rope. Okay, rope is a completely like concept that is related to embeddings part, right? We will talk about it at the last, but for now this is a short glimpse of exactly what is happening. Now if you want to understand the mathematics, I think I will have to make another video, but I think people who know about LoRa, right, they don't know that exactly what I'm talking about when you say low rank matrices, right? So they are applying that concept here, making the kV cache smaller, and that is making the inference faster and training smoother. Now, this whole advantage comes in two parts in the paper that they have mentioned in DeepSeek, right? That the whole concept that of low rank joint compression for attention key and value, this reduces the KV cache during inference. That is very obvious because you are already making the matrix small, right? And for attention queries during the training part, they have also performed a low rank compression. Okay, this can reduce the activation memory during training. So these are the two aspects, even during inference and during training. They are covering both the parts. This is helping a lot, right? Because if you understand from a inference point of view, it is helping you getting the answers faster, keeping the performance same. Similarly, when it comes to training, you're reducing the activation memory during training, and you are still getting the performance same. So just imagine it like a concept of LoRa, right? In LoRa, we were able to achieve the same level of accuracy as a full fine-tuned model, almost same, you can say, by actually keeping the computational cost and the whole thing, the timing and the resources less, right? So what could be better than that, right? So this is the whole concept of multi-head latent attention. Then came the concept of mixture of experts. So while studying this, right, I was rereading the papers, the two famous papers, right? The first one of my favorite, right? This mixture of experts paper, right? This was released by Mr. Lin on 8th Jan 2024. Interesting paper, right? And before that came this, the first time when I got to know about this sparse experts model in deep learning, right? It was released by Google. It was released on 4th September 2022. So these are some interesting papers. If you guys want to read them, I will highly recommend them because you'll learn a lot of new things from this paper, the top key thing and everything. So yeah, so I think we all know basic MOE, right? That we have tokens and we route them to a particular set of models, right? The FFN that we keep. I think I should not have said models, but yeah, I think you guys get to know. Okay, so we need to load balance, right? That two things, knowledge hybridity and redundancy. Now what are these two things? I have the traditional MOE, when we are talking about, it uses only selected parameters at a time, right? That you have some useful parameters that, okay, this is required for this particular token, and that particular parameters, that FFN will be used, right? The network that you have trained on, the 7 to 8 networks, let's say, have trained on, you are only going to pick, let's say, top k, then you are going to pick 1 and 2, let's say, for example, and the rest won't be used. Now, but while training, one expert can actually learn from other and forget things. That is one thing that can happen, right? Now, two things that are the problem here is knowledge hybridity and knowledge redundancy. Let's say in knowledge hybridity, let's say while training, the model has learned diverse knowledge, right? Each this feed forward networks, right, they have diverse set of knowledge. Let's say 7 models are there. Now you are only focusing on top k, let's say 2 models. The 5 models are completely useless here, sort of, right? Because you guys, we are not using their knowledge, even though they could have also provided some good input on that, right? Because the gate structure is trained in such a way. Now, second problem is knowledge redundancy. That let's say you have seven models, right, and you are training your whole architecture, right, the MOE architecture. In that case, because the 7 models are different, they are going to learn diverse set of knowledge, and there's a very good chance that you will have same set of knowledge set in all of them, right? So you see the overlap here, right? The whole concept of MOE can actually break using these two things occurring at once. But we need to load balance them, right? That we need to have a that we need to balance this also, and keeping all of them at same level, not having one above or low, right? So they came with the concept of DeepSeek MOE. Okay, so I think this example you guys should know that, let's say, let's say we have different FFN, right? Now in that case, let's say one expert actually likes biology, right? It learns biology, and the expert learns philosophy and then forgets what a cell is. So this is not good for an expert, right? Because you trained it specifically for biology, and then it learns about philosophy because of the diverse thing that is happening, and it forgets what a cell is, right? So they came with a concept of fine-grained experts. Okay, that okay, we are going to have these fine number of experts. Now it's an interesting concept. Just stay with me. Seeing the results, you will see here the number of activated parameters. That is very important in MOE because not all parameters are activated at once when you pass a token, right? But the performance totally depends on the parameters, right? We have this whole thing, right? The better the number of parameters, the better the model can be, but it doesn't work like that. I think most of the people know. Here if you see the average performance, DeepSeek MOE 16 billion is achieving the level of 7 billion, and just imagine only 1.5 billion parameters are activated at one time. Just imagine, sorry, 2.5 billion parameters, right? Now I don't know, like, that people, when they came with this whole concept, I don't know, a lot of companies did not use this, but I think for MOE part this was the whole thing, right? Using less parameters and getting the best performance. But I think a lot of people skip this paper, right? But DeepSeek MOE was a revolution in this part because they came up with two major things: fine grade expert segmentation and shared expert isolation. Let's come one by one. Let's say there you have a whole network, right? The first one, conventional top two routing, right? You have the input, you go to a router, you select the top k, that is 2, and you get the results from there, go to the hidden layer, okay? But what they say is ki, let's say you instead of having n number of these experts, let's distribute the expert, that is FNN, into m smaller experts. Okay, we are coming with this whole new variable m. Okay, anyways, each FFN is going to learn diverse set knowledge, so that why not having many experts, right? Because let's say you have 7 and you have, let's say you divide every FFN into 4. How many do you have? 28, right? So now you have 28 experts to take the input from, the options, right? That this whole combination, you have 28. Out of that you have to pick 2. That is far better than having this, right? And you can take multiple k. Now you don't need to have 2k only, you can take 4, 6, 8, 10. I won't say 10 obviously, but you can increase the number according to the number of experts that you have, right? So let's have multiple options for us, right? Let's say the current status, I'll show you. Taking 2 from 16, right? 2 from 16 experts is, you just have 120 combinations. But picking 2 from 64, right? It has 44 million combinations. Obviously, we won't be picking only 2. Maybe we can pick 4, right? And just give you an example. So this helps us a lot, right? Because if all the FMNs have diverse set of knowledge, and now you have multiple experts, not only 8, 9, 10. You are restricted to that, right? So it helps us a lot. Now coming to the next part, right? This shared expert isolation. I think I have took the exact part from the paper itself because I think they have done the best explanation possible. I'll just read it, and I think if you guys want to pause and read it, I think you guys will get to know what exactly they are trying to convey us, right? That with a conventional routing strategy, tokens assigned to different experts may need some common knowledge or information. As a result, multiple experts may converge in acquiring shared knowledge in their respective parameters that we have been talking about, right? They are now, the first problem is solved, right? That the knowledge hybridity. Now coming to the second problem, knowledge redundancy, right? Now we need to solve this. But however, if there are shared experts, right, dedicated to capturing and consolidating common knowledge across varying contexts, the parameter redundancy among other routed experts will be elevated. Simple as that, right? You will have some shared experts always with you. So this elevation of redundancy will contribute to more parameter efficient model with specialized experts. So towards this objective, in addition to the fine-grained expert segmentation, we further isolate key experts to serve as shared experts. Now, regardless of the router module, each token will be deterministically assigned to these shared experts in order to maintain a constant computational cost. The number of activated experts among the other routed will be decreased by k, as depicted in figure 2c. And I think I'll take you guys back. Yeah, here it is, right? If you see here, the output is here. You have this, and k is equal to 3, and you have a shared expert here. So now you've decreased this k from 4 to 3, right? Because you already have one shared expert for sure with you, right? Which has this diverse set of knowledge. So this knowledge redundancy part is also solved for you guys, right? A lot of things are solved, this whole thing. Now there are two more concepts: this expert level balance loss, device level balance loss in the load balancing consideration. I would pin down the paper in the description. You guys can go and read, because I think that is very simple and you guys will be able to understand that. And we can move to the next part, right? So now we have covered two things: multi-head latent attention. We have covered the whole concept of fine-grained experts, the DeepSeek MOE. Now we'll come to multi-token prediction. Coming to multi-token prediction, let's move ahead with the what is that. So currently we train models on next token prediction, right? That we train the model, okay, this is going to be the next token after particularly let's say dog comes is, and after is comes the, something like that, right? Now what this concept is that you need to train ML models to train and predict multiple tokens at once, right? Now think it as like this, right? Let's say you have a word X, then you have four words ahead of it. Now you are training that token like of predicting the four of all four words at the same time, right? So this is basically the whole training method, right? Using during inference you discard this, right? Use it, but usually in the paper itself they have said that we are discarding it. We are simply using next token prediction at that point because the training has already been done. Because think it like that, when you are understanding the whole flow as a LLM, you will are getting only one token at a time, and let's say for every token now you are getting four tokens at a time. Now how this is going to help you, you guys are now the LLM is able to get more context, right? Let's say instead of one you are getting four, six, eight, something like that, right? So yeah, this is the whole concept, and this is only using training. During training you are not using it during inference. You have an option, but yeah, you try, you can skip it, right? So this is going to obviously speed up the model to three times if you are going to use it, right? Because you are predicting x plus 3 tokens at the time, right? So yeah, now coming to the next part, this is the standard formula, right? Take this P as the language model, right? And you are implementing the next token prediction task. This is the whole basic formula that we already know about. Now below, you are training a large model as to maximize the probability of x t plus 1 for the future tokens, right? Given the past history of tokens that you have t 1 2 3 4, like something like t plus 1 2 3 4 5, right? So they have generalized this formula as you can see below. You can see instead of t plus 1 to t is to 1, you have this t plus n to t plus 1 ratio, right? That with t is to 1, right? So it's really simple, not that complex, but a lot of people, right, have shown that okay, this particular thing, right, multi-token prediction have helped them train the model in a better case, right? You're able to understand the situations, the nuances better than the current approach, right? And the two major things is it is memory efficient implementation during training, right? So that was a problem that was coming, and then you have the using next token prediction during inference. So it's boosting the performance, right? So if in a glimpse again, if we need to talk about it, so these techniques make the model understand the nuances better, and even during the training tasks, coding task, we have seen it giving better results, right? So it is making everything faster. It is making the model understand things better. So yeah, this is all in a glimpse about this whole paper, multi-token prediction that DeepSeek have used in this model, right? I'll pin down the paper in description. If you guys want to read about the method in more detail, we can have a separate video on that. I have briefed it down. You guys can go and read the paper. Okay, now the major advantages we have already talked about. It is using self-speculative decoding, that is making the inference much faster, and it is learning global patterns with multi-token prediction, right? They in the paper itself, if you guys go and read, they are even doing multi-token bytes, right? Instead of the words, they're using bytes for that, and even in that they're seeing so good results, right? Now comes the next part, quantization, right? I think we have already reached the video of 20-25 minutes, so I'll try to keep these things bit brief. And yeah, so this is the overall current architecture, right? I think a lot of people know that we have multiple type of quantization. We have 4-bit, then we have 8-bit, we even have 2-bit, right? But we know that when we are quantizing, we are seeing that our performance is not going to remain as same as the natural model was, right? So they have come up with this concept of fine-grained quantization, right? To mitigate this quantization error caused by this feature outliers, right? So for this particular segment, let's say for this diagram, you guys can understand it in such a way, right? That for activation part, they are only grouping and scaling the elements on 1 by 28. From what I can see in the paper, they are grouping it by 1 into 28 tile pieces, right? Now for the weights part, what they have mentioned in the paper, that they are going with 128 by 128 block basis, okay? So they're keeping it separate, right? And now this whole approach, quantization, this whole approach of quantization, this fine-grained quantization is ensuring that the quantization process can better accommodate outliers, discussed during training. So yeah, that was it for this quantization part. It's not that big, but I thought I should cover this particular part. Okay, now rope, I think a lot of people, I think, have already discussed about rope in these videos, and I think I have the paper with me. Let's see. So this paper, rope, right, one of the best papers in the past 2 years. which talks about, that the whole positional encoding thing that we have already talked about are the main basic building blocks of LLM, right? Now, what they say is that it encodes the absolute position with a rotational matrix, right? And meanwhile incorporates the explicit relative position dependency in self-attention formulation. So it's I think I have written some particular notes to make things easy for you guys, so that, and guys, I am going to give you a website where you can go and test this whole ropes thing and see how it works visually, right? Because when we understand things visually, it helps us a lot, right? Understanding the complex part into smaller segments. So if we go through the papers, right, they have come up with this whole distance things, that they have clipped the relative distance, right, with the hypothesis that this precise relative positional information is not useful beyond a certain distance. Okay, this hypothesis they have done, and through mathematics in the paper you guys can see they have proved it, right? And in a whole glimpse, right, this current pseudo positional encoding have come up with this basic formulas that we already know, right? We have the sine and cos and the 2i plus 1 and 2i, right? So this whole concept was working well, nothing was a problem. But then they come up with a concept of rope, right, that you can do a step by step complex computation for a particular matrix by rotating it, right? So the formula differs a bit. In now you have x position, the position of, let's say, x multiplied by the cos theta of that position, plus the x of particular position multiplied by the sine theta of that position, right? So it's a pretty straightforward, and if you look at the results, they have achieved better than the current embeddings that we have, right? The current sinusoidal embeddings, the Wobert and the row formers say that we are achieving 66%, which is better than the BERT. And that is why you will see that a lot of big models, right, llama 3.1, and everyone is using rope in their models, right? And if you want to visualize rope, I'll pin down the visualization website. It's a very good website, that blog, you guys can go and read it. Okay, so in a glimpse I want to tell, initial embeddings start with, for token a and b, let's say xa plus nxb in a 2D space, right? You can see this, right? And then for each token you calculate a rotational angle theta a and theta b based on their respective position in the sequence. Now the third part, it comes here, right? Yeah, where you are going to rotate each token embedding vectors by corresponding angles. Let's say this was the one, so you're rotating it, right? Now this is done through element wise multiplication by cosine and sine angles, the formula that we discussed previously, right? That the sine theta of that particular multiplied by xa. Now this rotated new positions xa and xb that you have rotated now contain both original and relative positional information, enabling the model to understand the sequence better. Now, coming to why exactly someone thought it is going to work, why is it still working except for the mathematical part, right? So they also say in the paper, right, that this is one of the limitation of their work, that they have not come up with a very faithful explanation, even though mathematically they are able to prove it, but not exactly that why is it working out, right? So yeah. Now let's look at some of the results of DeepSeek-V3 model, how it is performing. It looks good here. If you see on the English test, DeepSeek-V2 base was giving, I think, yeah, if you look at natural quotient 38.6, but DeepSeek base V3 gives 40. Similarly, this trivia QA 82.9, good, right? And in all of the others, if you look at Llama 3.1 405 billion base, other models, it is outperforming everyone, literally everyone, right? So the average is multilingual also 79.5. 82.7 on this Chinese. Mathematics outperforming everyone in the market, all the open source that exist. Now, if we will be comparing big models like GPT-4o and Claude 3.5 Sonnet with R1, because R1 is even a model which can reason, think, and then answer, right? It is not fair to compare O1 and O3 with this particular V3 model, right? So yeah. Now in this needle and a haystack, right? When you think about RAG, in RAG we need to get a particular answer from a chunk of pile of answers, right? In this, they are saying that it is getting 10 everywhere, right? Depending on context length or document depth percent. Okay, this is bit interesting, and also will put a question in someone's mind, right? Are these numbers okay? Personally, I have not tested DeepSeek V3 on this particular part, but maybe it is performing good. We still need to evaluate, right? Yeah. So yeah, that was it for the video, guys. I think we have covered all the 5 segments. I'm sorry if at the end I took all the things in a bit brief segment, but I just don't want to keep the video too long, because I've seen in my previous videos people don't stick to the video if you're making it too long, right? So I wanted to keep it short, precise, and crisp, right? That you guys get to know, okay, what are the major 3 points which are special about DeepSeek V3. So if you guys want, we can make a separate video on any particular concept that you guys want to study in detail. So yeah guys, that was it for the video. Thank you for watching the video. Thank you and have a nice day.